Alright, hello everyone. So, hopefully you're already in your seats and working on your do now. We have limited time today, so you're going to have 2 minutes. Actually, you know what? Let's make it 3 minutes. 3 minutes to go ahead and continue working through this do now. You can go ahead and pause the video here. Alright, so we're going to kind of go over only a couple of these values in the interest of time, but we're going to start with -2. So what we're being asked to do is we want to evaluate f of -2. We're given a function here, and eventually we're going to go ahead and graph it. So let's start with -2. So I'm simply going to take -2 and plug it in for every single x that we have, because when we're given an input, that's exactly what it tells us to do. So we're going to have 2 times -2 minus 3. This is going to give us 2 times -2 is going to be a -4 minus 3 for a -7. So I'm going to go ahead over here and I'm going to put -7. Perfect. And then I'm going to do -1 as well. I'm going to have the f of -1, and again, it's the same exact process. It's going to be equal to 2 times -1 minus 3. So we're going to have -2 minus 3, which is going to end up giving us -5. So I know right here we have -5. Now going through these, hopefully you found that for f of 0 we should be ending up with -3. For f of 1 we should be ending up with -1. And for f of 2 we should be ending up with a +1. Now if you calculated those algebraically and wanted to really double check, remember exactly what this function is actually made up of, right? We have this 2x minus 3, where this 2 is our slope, right? This is our lovely m value, which means that every time we hop down here, we should be adding 2 every single time. In fact, we are. Perfect. So we're all set and good to go. And so moving on, our graph, we would simply take all these and we're going to make our points. Remember that this is our input, this is our output, so that's how we create our points. And so we're going to have -2, -7, -5, or sorry, -1, -5, and so on and so forth, going all the way down this list. And we simply just go ahead and plot these. So we're going to have one about there, and then we move up to right here, and then we've got one right about here, with our last one going right about here. So our line is going to look something like that. All right, and then quickly looking at number 2, we're just being asked to state the domain and range of this function. Well, first thing I have to do, I have this point right here, and hopefully these graph lines came out. I know that they can be a little hard to read when they get copied, but I can see, hey, you know what, this is going to be -1, 8. Ooh, there we go. So that point is -1, 8. And because that point is -1, 8, I know that the domain of this, right, remember that domain is our input, or our x values, I know that I start at -1 and I go on to the right forever, right? And remember that when we have this, we're going to say that it's implied that we have an arrow there. So I know that, hey, my x simply has to be greater than or equal to -1. And so looking now at my range, which is, again, remember from yesterday, it's my output, or my y value, I know that we start at -8 and then we go down infinitely, right? We never stop going down, or sorry, we go from +8 and we go down infinitely. We never stop going down. So I know that y needs to be less than or equal to 8. And so very simply, those are my domain and ranges. Because remember, when we're looking at domain and range, we're really looking for what restrictions is this graph going to have? That's really the question we want to have in the back of our mind when we're answering domain and range questions. All right, take 30 seconds, go ahead and pause the video if you need to. Make sure you have this all down, then we're going to move on. All right, so coming back, we have just one example on our notes today. It's going to be quick. Example 1 says that the function f of x contains the points f of 2 is equal to 9 and f of 0 is equal to 5. So we need to determine the equation of f of x. Now this kind of combines what we learned about function notation and what we've been doing with lines for the past few weeks and kind of puts it all together. So hopefully when looking at this, we should notice, hey, we have an input and an output, and we have an input and an output. So this is my input, this is my output, this is my input, and this is my output. And so what that really means is that I can write these as coordinate pairs. So I'm going to have 2, 9 and 0, 5. And as soon as I have those two coordinate pairs, I know exactly how to find the equation of a line. So I'm going to go ahead and label this x1, y1, x2, y2. And then I'm going to go ahead and perform my slope calculation the same as I would for anything else. So I'm going to have that 5 minus 9 over 0 minus 2 is going to be equal to, well, 5 minus 9 is going to be negative 4 over 0 minus 2 for a negative 2, which is going to give me a positive 2 when we reduce this. So that my slope is equal to a positive 2. And now there are two ways to make a line, right? Or actually there's a few ways, but we have two really prominent ways that we've used a lot. We have point slope, which you can use, but we also have slope-intercept form. And it's important to know that we can actually use slope-intercept form because we have this lovely point right here. We have 0, 5. And we know that whenever x is 0, that y-coordinate is our slope, or sorry, our y-intercept. So this is our b value. So because of this, hey, I know that my b value is equal to positive 5. And so if I'm building f of x, I'm simply going to use that f of x is equal to 2x plus 5, not b. Well, it is b, but we know that that b is 5, so 2x plus 5. And this is my equation. We're actually going to skip over graphing it today. Again, just sort of in the name of time. When I originally created this packet, I had forgotten that today is a half day. Yes, very exciting. So we're actually going to skip graphing it, and we're going to go right on down to C, where we need to evaluate f of 4 graphically or algebraically. Now, obviously, we didn't graph it, so this one's kind of taken off the table. So we're going to work on finding it algebraically. So just as I did in our do now, we're going to go ahead and we simply plug this in for all of our x's. So we're going to have 2 times 4 plus 5. So I know that 2 times 4 is going to be equal to 8 plus 5. And so I know that f of 4 is going to be equal to 13. And so now, down on D, it says to determine the domain and range of f of x. Well, it comes back to that question. If I'm looking at this function right here, 2x plus 5, I should be thinking where or how is this going to be restricted? And looking at this, we should hopefully be able to recognize that there aren't any restrictions. There are no restrictions on what x can be, and therefore no restrictions on what y can be. So I know that my domain is going to be equal to all real numbers. And likewise, my range is also all real numbers. And so down in our everybody writes section, we have just sort of one follow-up question. And it says, what if the function f of x represents the weight of a baby as they grow over the course of t weeks? Would our domain and range change? Why or why not? Right, so there is admittedly a slight typo. This should be a t. So it should be f of t, right? Because we have t weeks. But we're being asked, hey, when given context, does this actually change our domain and our range? And like we sort of touched upon yesterday, hopefully you look at this and you remember, well, I know that measurements, there are certain things that you just can't have negative numbers, right? Measurements, time, doesn't really make sense. So if we're thinking about the domain and range of this new problem with its new context, we would need to think, does it make sense for t to ever be negative? Well, no, it doesn't. So if it doesn't make sense for t to be negative, it changes our domain, right? Changes our domain where t is greater than or equal to 0. As long as t is positive or 0, we have no problems. And so for our range, we have to have that same conversation with ourselves. My range now represents the weight of a baby. Now again, this f of t value is not going to make any sense if we have negative, right? You can't have a negative weight. You can lose weight, but when you get on a scale, you're never going to see a negative number. And so for that reason, we know that f of t also has to be greater than or equal to 0. So it will change, and the reason that it changes is because negative numbers just don't make sense given this context. And it's as simple as that. So go ahead, I know we just went over a lot. Go ahead, pause the video here if you need to. Make sure you have all this down. And then we're going to continue with some independent practice. All right, so you're going to turn to problems today. Hopefully you're already there. But you're going to go through, you're going to do all problems today, right? It's 3 parts. You have A, B, and C. All 3 parts use this lovely graph right up top. For these 3 parts, you're going to have 6 minutes, silent and solo. Go ahead and get started. And you can pause the video here. All right, so in part A, we're told, hey, write the equation of g of x. Well, perfect. I know from up above that I have a few ways to do this, and from the past few weeks, we have multiple ways to do this. I'm given a line. I'm going to pick 2 points that suit my interests. So I'm going to pick a point right here, and I'm going to pick this point right here. So down here, we're going to have 0, -1. And up here, we're going to have 1, 1. And so when writing the equation of g of x, I have to start with my slope. And so I know that my slope is going to be equal to 1 minus a -1 over 1 minus 0, which is going to be equal to, well, 1 plus 1 is 2 over 1, which is equal to 2. And so I have my slope, and then once again, I've picked this value really specifically because I know that this value is my y-intercept because this lovely x-coordinate is 0. So I know that this is going to cause my b value to be equal to -1. So building this, I know that g of x is equal to 2x minus 1. And so part B says graphically or algebraically evaluate g of 2 or when g of x is equal to 17. Now, for g of 2, that's something we can definitely just use this graph for, right? We go right to 2, because remember that we're being given an input here. So we go right over to 2. We go up to find where our line is. We find this point. I know that my line is hitting right here at 3, right? Because this point is fully 2, 3. So I know, hey, you know what? Using this graph, g of 2 is equal to 3. And now looking at g of 17, this, remember, is an output. And so I'm being given an output of 17. Now normally if we were given an output, we would kind of go find where that is on that y-axis, draw our lovely line, and see where it's connecting and crossing and intersecting the graph of the, or sorry, the line of the graph or the line of the function. Our scale doesn't go up that high. Our scale only goes to 5. So it doesn't make sense for us to try and do this graphically because it's going to be physically impossible. So we have to do this one algebraically. And so we're given an output. I know that I'm going to substitute 17 in for g of x using this equation right here. And so I'm going to have that 17 is equal to 2x minus 1. I'm going to add 1 to both sides to have that 18 is equal to 2x. And then I'm going to multiply both sides by 1/2. And I'm going to learn that 9 is equal to x, specifically when g of x is equal to 17. All right, and then part C, identify the domain and range of g of x. Well, again, we ask ourselves that lovely question is, hey, is there anything going on that's actually going to restrict what I can possibly have for inputs or outputs. And looking at this, I see I have arrows. I know it's going all the way down forever and all the way up forever. So no, there's no restrictions going on in this. So I know that, hey, for both of these, it's going to be all real numbers. The domain and range for this function will be all real numbers. Now, for a lot of what we're going to be looking at, we're going to find that it's all real numbers probably more often than not. Because whenever we're looking at something that's just going to be a classic line with no hiccups, anything that's linear is generally, as long as there's no starting or stopping point being noted, generally going to be all real numbers for our domain and range. It's not until we start to get into higher powers or really specific start and stop points that we see that these can kind of become really interesting. All right, so again, go ahead and pause this if you need to. Make sure you have this all down. And from here, depending on how much time you have left, because today is a slightly modified day, if you have time, go on, get some more practice with problem set B. Problem set B is really, really good. Whoever's filling in for me will have the answer key and be able to answer any questions you have. Otherwise, go ahead and start your exit ticket. Your exit ticket is 3 parts. I want you to try and do all 3 parts. It should be, hopefully, things that are familiar, things that we've seen before. We're just starting to kind of add everything here into the mix. And an important note, you do have homework. You do have homework. Your homework is, I know it says 2 questions. Obviously, you have a few things going on in here. But again, it's just using this lovely graph to find some values. So again, depending on where you are, go ahead and get some more practice. Otherwise, go ahead and start your exit ticket. Tomorrow is Thursday. Remember, we do not have school tomorrow. Do not show up. We will not be here. And I look forward to seeing you finally again in person on Friday.